convert back. So from log form over to exponential form. And this is one where, again, you can just look at it and read it as a question. 2 to the 1 is 32, 5. 2 to the 1 is 4, 2. 2 to the 1 is 1/8, -3. 2 to the 1 is 1, 0. So you can again practice that. But what we really want to do is convert log form to exponential form. So again, what would be helpful to memorize is left to the right equals middle. Left to the right equals middle. So that's 2 to the x equals 32. Left to the right equals middle. So log base 2 of 4 equals x. Left to the right equals middle. 2 to the x equals 4. Left to the right equals middle. 2 to the x equals 1/8. Give that a shot. Try saying that in your head, or try saying it under your breath. Left to the right equals middle. Left to the right equals middle. Ah, very good, Emily. Good catch. Didn't get to any and left the top.
Nice work. Awesome.
Nice. All right, folks. So you've had practice now converting from exponential form to log form, and even practicing some of those math facts we learned on page 1. So again, we have exponential form, which is b to the e a, and then we have log form, which is log base b of a e. And the fact that we want to convert back and forth between them by switching the order. Just E and A are the only two that switch, because B is always the first number in both expressions. And then trying to answer them off the top of your head. Again, the goal is just to be able to try to answer them off the top of your head. There are certain numbers that we see over and over again in math problems, and so it's helpful to build that familiarity with powers of 2, powers of 3, powers of 5, and powers of 10. Any questions you want to ask right now? Okay, turn the page and let's take a look here about your calculator. So let's learn about your calculator. On your calculator, you have 2 log buttons. Go ahead and try to see them on your calculator. One is log, and directly below it, I think, is ln. Okay, so the log button means you're solving the problem of the form 10 to the x equals n, where n is just some positive number, right? It has to be a positive number. I'll go ahead and write plus n. So you can, using the log button, you can solve any equation of the form 10 to the x equals n. And so, as we previously did, if you wanted to solve 10 to the x equals 50, you would be log base 10 of 50 equals x. And the answer that your calculator gives you is the exponent. Now notice that your button, does your button say log base little 10? No. So what you need to know is that the mere letters log means log base 10. It's assumed. Here's the really terrible news. It's assumed log base 10 in all the classes that you would take through your undergraduate career. And then all of a sudden later on, like mathematicians at higher levels only ever use the other log button, and then log is assumed the other log. It's terrible. Let me just finish this. I should have defined this first. So now you have an ln button. What is ln? Ln button solves any problem of the form e to the x equals a positive number. Well, that begs the question, what is e? What? Not any number, that would be nice. No, E represents a very specific number. Maybe you've heard of it, maybe you haven't. Just to give an example, everybody has heard of the number pi. Right? Pi is the number of 3.141592655, and so on. So pi is a number we're all familiar with. Does anyone know what pi is?
It's just something you eat. You go first, like. You go first.
I was going to say something you eat. Pi is something you eat.
Yes, exactly. Something you eat, Hector. What is pi? It refers to the circumference. In fact, it's very easy to capture in simple English. Pi, 3.14, is the number of times the diameter will wrap around its own circle. That's it. The answer is if you took the diameter and started wrapping it around its own circle, it would wrap around 3 and a bit.
And the diameter is not wrapped around.
What?
The diameter is wrapped around.
Right, 3.14 diameters will wrap around a circle. It's always the same.
So like the digits, like how many digits have we done far back? Because I know it's like just kind of complex.
Oh, yeah, sure. Well, I mean, there's infinitely many digits of pi. Yeah. Okay, so that's what pi is. It's the number of times the diameter will wrap around its own circle. E is a different number that has nothing to do with a circle, but it's another famous infinitely long number. So everybody, let's find the number E on your calculator. Go down to the ln button, and what do you see right above it in writing? E to the x. So there's the e to the x right there. Let's call upon e to the x, so hit second ln, and then your screen says e to the, and just put the number 1, because we want e to the first power. E to the first power is just e. So what is e? Hit enter.
2.71.
Yeah, 2.7182818288, and so on. Now, there is no simple physical explanation of what E is. It's not the number of times the diameter wraps around something. What E is a number that is intimately related with natural growth and decay processes. Natural growth and decay. This is when we most use the letter E. So what are natural growth processes? Natural growth.
Trees.
Trees? Yeah. Any living creatures that grow. Specifically, we often talk about bacterial growth. You drop one bacteria on your friend's pizza, and then wait a while. The bacteria will grow, and infest his pizza, and then he eats it and he gets sick. Well, that's natural growth, because bacteria will just start growing rapidly, doubling and doubling and doubling. So that's yep. And a natural decay process would be radioactivity. So you have a sample of radioactive uranium. It's not going to stay radioactive forever. It's going to decay and decay and decay, and eventually that uranium will no longer be radioactive. You just have to wait a couple billion years. So natural decay like radioactive materials and natural growth like the growth of living organisms. So when we model those things, we often use the function e to the x. Okay, so there's e, and so the ln button is going to solve any function of e to the something equals a number. So if you wanted to solve e to the x equals 50, then you would type in ln of 50 equals x. And so, again, ln actually means log base e. So take a look there. Those are the only two bases your calculator knows. Your calculator knows log base 10 and log base e, and that's it. Which means your calculator can solve problems 10 to the x equals n, and it can solve problems e to the x equals n. But that's the only thing your calculator knows how to solve. We have a calculator trick that will allow us to solve other bases. So once we study this a little bit, we'd be able to solve 2 to the x equals n, but your calculator doesn't actually have a button log base 2. To be fair, no one with a TI-80 something has a button that says log base 2. There are calculators like Casio's that actually have buttons where you can type log base something. But most of us don't have that calculator. Okay, so folks, when you type log 100 in your calculator, what you're really doing is log base 10 of 100. And now we can all read that as a question. 10 to the what is 100? 2. And your calculator will say 2. When you type log 1000 into your calculator, you really are doing log base 10 of 1000. And we can all answer that question. 10 to the what is 1000? 3. And when you type log 50 in your calculator, you're really doing log base 10 of 50, which means 10 to the what is 50, and we previously saw that as 1.6. And so on. Okay. Now I have to move my board up to right on the last section. No, finish right there. So likewise, when you type in ln into your calculator, so when you type in ln, what you're really doing is log base e of e squared. And when you're doing ln, that's really log base e of 10. When you do ln of 100, that's really log base e of 100. Which we can type those into the calculator and see what they are. Doesn't really matter. Just wanted to make sure you all knew what ln means. Now, what does ln mean? What? ln. Huh? Oh, ln, yeah, ln, the TV show. ln stands for, it's either Latin or French, logarithme naturel. There's not a consensus on why that was chosen or what language it's supposed to represent, but the first person to use it was in 1993. I think his name was Swingham. Not that it matters, just give historical context, but it's probably that, like logarithm naturel or logarithmus naturalis. So the point is that it's ln as opposed to natural logarithm, would probably sound better than natural logarithm. But NL, that'd be a little misleading because we want it to be log, L for log, so it's LN, log naturalis. Okay, well, those are our calculator buttons. We will proceed to learn how they work. And got one more big idea here. And the last big idea on the last page is that the graphs of log and ln are inverses. So these are inverse functions. Now, since they're inverse functions, what should we see when we graph them? There should be a mirror image. So let's take a look. I'm going to go ahead and graph it. You can just kind of sketch your own graph. So here's my graph. And here's my line. So what should we expect to see? Can you already kind of turn your head to the right and kind of imagine what the other graph should look like? I'm going to type in log of x. And sure enough, they are inverses. So 10 to the x and log x are inverse functions. And we can go ahead and verify that for ourselves right here. What if I did 10 to the x, so f of x equals 10 to the x, and f of x, f inverse of x. Well, hold on, I'm just going to write that. F of x equals log of x. Remember, if two things are inverses, it should reverse the order of input output. So if I do the input 3, what's my output? 10 cubed is 1,000. Whereas now over here, if I input 1,000, which is log of 1,000, who remembers what log of 1,000 is? You can type it in your calculator. 10 to the 1 is 1,000. 3. So they really do reverse the order of input output. So 10 to the x and log x, those are inverses. Likewise, e to the x and natural log of x are also inverses. And in general, 2 to the x and log base 2 of x are also inverses. So whatever you make the base of the exponent, make it the base of the log, and those are going to be inverse functions. Alrighty. That's where we are so far. What questions would you like to ask? Yeah.
I'm joking.
Okay, let's time travel back. We'll do it again.
Are we, so you said we don't have anything on our calculator by the end of the section?
You'll be able to do it with your calculator. Yeah. So what we just accomplished, folks, is to introduce the idea of logarithms and some of the main concepts about logarithms. You notice we haven't actually solved anything in particular, other than how to convert back and forth between log form and exponential form, and the fact that these are inverses of each other. Yes?
Do you know, like, real world applications or like what they can be used for?
Yeah, absolutely. I mean, as I just mentioned, you would use e to the x for any natural growth or decay processes. So it's basically modeling.
Okay.
Anytime you want to model anything that happens in the real world, let alone money, perhaps you all have seen the formula A equals P 1 plus R over N to the NT. That's compound interest. And so let's say that you're getting interest compounded monthly. Then that means that however much money you invest, say $1,000, and you're going to compound monthly at an interest rate, let's say the interest rate was 5%, and you're compounding monthly, which means N is 12, so monthly, 12 times a year, you're going to get some interest. And let's say you invest $1,000 at 5%, getting monthly interest for the next 10 years. Then that's going to tell you how much money you have at the end of 10 years. Again, looking at all these parts, you invest $1,000 at 5% interest for 10 years, and you're getting monthly interest, 12 times your interest. So something you could do then is you could say, let's say that I invest $1,000, again, for 5% interest, and I'm getting it monthly, and I'd like to know, how long do I have to wait time until I double my money? Okay, so you're saying, I'm going to invest $1,000 now. I want to eventually have $2,000. I know I'm investing at 5%, 12 times a month, or 12 times a year I get interest. Solve for t. Well, now notice, where's t? It's in the exponent. So you would need a logarithm to solve this problem. So simply asking the question, how long do I have to wait to double my money, is a logarithm question. So that's one nice simple example I can give you right there. Same thing goes with populations. Let's say you have a population of people or bacteria or any population, and you're watching it grow. You can say, how long until the population reaches 1 million? Again, that would be an exponential.
Those are the ones that I've seen.
Or decreasing in population.
Or decreasing population, or radioactive material. You could say, this radioactive material is not safe until it only is at a level of 10% or less. So how long do we have to wait until it's safe? So all of those questions are logarithm questions because you're solving for time, which is in the exponent. Does that answer your question? Okay. Okay, so everybody take a look at your packet here, chapter 6. Now, there's a whole lot of information in the next 1, 2, 3 pages, I think. We're not necessarily going to read that line by line together, but I always encourage you to kind of go back and take a look at it and see what they say. So we've got some information there. You'll notice that they're showing you the inverse functions symmetric across the diagonal line, and then they're giving us all sorts of properties about logarithms. Take a look at the next page. So what is this, page 3? Okay, page 4. Page 4, all of you can already solve. So I think this would be fun to go ahead and try to sit down and solve these right now. For instance, right, it says, example, rewrite the exponential as logarithmic, and then write the logarithmic as exponential. So they're just asking you to switch it, which is what we've already practiced. So everybody go ahead, try switching these around. You don't actually have to solve anything or compute anything. They just want you to write it in the other language. And when you're done doing it on your own, you can look up and check your answer. This is really good practice converting back and forth between exponential and logarithmic. Because what you're doing right now is just a definition. It's just a definition. We're not really solving anything per se. You're just rearranging something. What you're doing is translating it from one language to another. Well, you can continue. I was going to continue on after that. My only thought would be to make that e smaller and more. But it's an obvious solution. Yeah, that's not a method. And see, maybe you're just writing quickly, like that one, and that's an and e should be a little more than So you're already writing your log. You have some small thing, right? So that E should not be the same size as your G over L. All those letters right now appear to be the same font size. So if your LOG is that size, E should be teeny tiny and low down. Does that make sense? Try it. Write it again and write log, and then put the E really far down and tiny. Yeah, there you go. And then and make that one longer as small as that L. So make that one smaller. Make the one, yeah. There, now that's looking better. See, you want the one to be the same size font as the log, and it keeps tiny. Don't worry, you might feel like I'm just being nitpicky right here, but it's gotta be, can I say it? It's gotta be like an obvious, so LOG this size. And I can't make my E the same size as my L. My E would have to be smaller than my L, so then my E would. Now, do you agree that my E is smaller than my O? Whereas if I did that again, you see how big my O is? If I made my E that big, my E is not the same size as my O. That's not a joke. It's got to be smaller than whatever size of writing that you're doing in the first place. Yeah, and since, like I said, since your letters are already pretty small, you want to make your E big and small.
Right.
Yeah, that's right.
I'm so glad.
No, you got it.
Okay, this one.
No. Right, we'll talk about that one next. It's assumed. It's like we were saying about the calculator button. It's an assumed base. We'll fill it in together. Okay, that's good. Everybody take a look at the answers on the board. I think everybody's just about done with the beginning part anyway. Just a couple to kind of note. Look at this one here. Log base E of 1 equals 0. How could we rewrite log base E? ln. So that's really ln of 1 equals 0. And you would just see ln 1. You wouldn't see a base. Ln has the assumed base of E. So you can rewrite that as ln 1. And then furthermore, right here, what's the base of this log?
10.
A 10, assumed. We assume it's 10 because they didn't write it. So this is really log base 10 of 100 equals 2. Which means now to convert this from log form to exponential form, it'd be left to the right equals middle, 10 squared equals 100. So if you don't see the base, it's a 10. Whereas here, ln, we don't see the base because that's actually log base E of E equals 1. Now folks, notice, is the size of this E the same as the size of this L? Yeah. And that's how it should be. The number that you're inputting into the log should be the same font size as the word log. The base should be teeny tiny. Can you tell that that E is smaller than that E? The base should be teeny and down below it should not be the same font size as the rest of everything else you do. So, because it just leads to confusion. Like if you had log E, I don't know if you're doing math or you're just excited, writing log E. Like, yeah, so it's got to be a small substrate. Okay, so now you can convert this left to the right equals middle, E to the power of 1 equals E, which is an obvious fact. Of course, that's an obvious fact too. 10 squared equals 100. Okay, well, very good. So that's rewriting the expression using the definition. Everybody turn the page. And here, they're asking you to evaluate the expression. These are exciting. Maybe let's do these as a group. I'll go around and call on them. You can have that piece of paper out in front of you, the one that you wrote things down on. But we might also have to just think about some of these. Now in mathematics, I really try not to use the method called think about it. Right? That can lead to a lot of pain and hardship. We don't want to have to think too much. We just want to use definitions and rules and apply them. So this first one, we should all be able to do because it was on the first page. So 3 to the 1 is 27. 3. So the answer is 3. And then how about the next one? 2 to the what is 32. 5. Now this next one we didn't do, but we can all think about it. So we have a base 6. So if you wanted to, you could really quickly say, okay, 6 to the 1 is 6, and 6 to the 2 is 36. You could build that same sheet that we built before, and then 6 to the 0 is 1, and then 6 to the negative 1 is 1/6, and 6 to the negative 2 is 1/36. So you see how I built it the exact same way as page 1? So now everybody can tell me 6 to the what is 136? -2. You probably, if you sat long enough and looked at the right part of the ceiling, you might have been able to just do that in your head. But only if you're looking at the right part of the ceiling. You know, some parts of the ceiling have the answers and other parts don't. Okay. What about this now? Ooh. Log base 8 of 4. Log base 8 of 4. How would we go about evaluating that expression? Let's think about what it said. 8 to the what equals 4? We could sandwich it. 8 to the 1 is 8, but 8 to the 0 is 1. So I know my answer is between 0 and 1. 1/2, we can try 1/2. 8 to the 1/2 is actually the square root of 8, which would be like 2.8 or 9, you know, something along those lines. Yeah, maybe 2/3. So what would we have to do? Sit there and play around with it for a while. Sit there and play. Now, actually, I'm going to show you something real quick, folks. Everybody watch this. This is going to blow your mind. Everyone's going to be really excited. Because right now we're thinking, oh man, we got to do the sandwich technique, super lame, take a long time. But everybody rewrite this. What we're really saying here is log base 8 of 4 is equal to what? We're asking a question. What is that thing equal to? So we take this logarithmic form. This is very important. Everybody write this down. Here's an excellent example of what we're talking about. Actually, you would? Yeah. Okay. So log base 8 of 4. We're like, hey, what's that? I don't know. Set it equal to x. Because now I can convert from logarithmic form to exponential form. This is really 8 to the x equals 4. Everybody wants this. It's really, really fun. It's really fun. What's 8 as a power of 2? Yeah, 2 cubed, right? So rewrite this as 2 cubed to the power of x. Now over here, what's 4 as a power of 2? 2 squared. Okay. Now, by our exponent rules, what do you get when you do 2 to the power of 3 to the power of x? What do you do with the 3 and the x? Not add. Multiply. So now we have 2 to the 3x equals 2 to the 2. Now look what we just did. I rewrote the original problem of 8 to the x equals 4 as 2 to the 3x equals 2 to the 2. Now, if I want these two sides to be equal to each other, first of all, they're both a base of 2, right? So whatever is underneath my thumbs must be the same. Like, do you agree that if these two, if the left-hand side and the right-hand side are going to be equal, and they're both a base of 2, then whatever's underneath my thumbs, it better be the same number. So what does that tell us about what 3x must be compared to 2? They must be the same. It must be the case that 3x is equal to 2. It must be. If I want these two, if I want this equation to actually hold, I need that 3x to be a 2, because then we'd have the same thing on both sides. So now finish solving for x. X equals 2/3. Wait, did you guess that, Gabe? Oh snap! Was that just a guess?
Yeah.
Okay. Well, hey.
I figured like if it's 1/2.
Oh, sure, yeah. Mm-hmm. So, folks, let's try it. On your calculator, type in 8 to the power of 2/3. See what happens. 8 to the power of 2/3. See what you get if you raise 8 to the power of 2/3. Snap.
Nice work.
Yeah, that's incredible, right? This is really interesting. We just calculated what log base 8 of 4 is. It's actually equal to 0.66666 repeating. Right? So that's the technique we'll be using. I just kind of casually introduced us to it right now. But that is a technique that we'll do is you rewrite both sides as a common base. That's what that's called. Rewrite both bases as a common base, because then you can set the exponents equal to each other. We'll do more of those, don't you worry. That's not the only one we do. Okay, this next one is more into something we can do. Let's take a look at this. Log base of 5 of 625. Now, face value, that looks crazy. Now, what are we really saying? Again, in math, you can always say, what is this thing? I don't know. Set it equal to x. Because now we can say left to the right equals middle. 1/5 to the power of what should equal 625? Where do you figure this out? Because first of all, you should all recognize the number 625. What is it? It's a power of 5, and it's really what? 5 to the power of 4. So now what I have is 1/5 to the what equals 5 to the 4. Well, how can I rewrite this 1/5 as 5? Because this 1/5 is the reciprocal of 5. So couldn't I rewrite that as 5 to the negative x? Because all I wanted to do is just take the reciprocal of 1/5, and you're allowed to do that, folks. If you want to take the reciprocal of a number, just take the reciprocal and change the exponent to a negative. So now I have 5 to the negative x equals 5 to the 4. Same thing, we just rewrote the base so that they're equal. So if 5 to the negative x has any prayer of equaling 5 to the 4, what must negative x and 4 be? Right, that's what we will do, but the fact is negative x must be equal to 4. It must be the case that negative x is equal to 4, which means x is equal to negative 4. And so we just calculated what log base 1/5 of 625 is. This is this is an advanced technique. We're just diving into it, showing you how to manipulate expressions. And you can check your work. You can go ahead and do 1/5 to the power of negative 4. Try it on your calculator. Type in parenthesis 1 divided by 5, parenthesis, caret, parenthesis 1, oh no, parenthesis negative 4. See what 1/5 to the power of negative 4 is. Yeah, better be 625. All right, well, very nice, folks. Let's try another one. And then I think it's almost time to go. Log 0.01. So first of all, what log is that? It's base 10. So let's rewrite that. That's log base 10 of 0.01. And I'm wondering, what does that equal to? So I set it equal to x, because I'm asking the question, what does that equal to? So now I can rewrite this. That's left to the right equals middle. So now I have 10 to the x equals 0.01. Well, what is 0.01? You can all tell me from the front side of your sheet. Look at the front side of your sheet, page 1. What was 10 to the what is 0.01? 10 to the negative 2. So you see that? We just kind of manipulated that expression until we got to something that we can now just read straight off. If 10 to the something is equal to 10 to something, the x and the negative 2 must be equal to each other. And so we just write down x must be negative 2. That must be the case. If we want those two sides to equal each other, the exponents must be the same. And even better, you can all type that into your calculator to see what you get. Type in log 0.01. It better be. Did you already do it? Oh, you already did it. Okay. So good. Well, this is really good. You see, we're getting a little bit of experience at manipulating expressions. This one right here, this is a wonderful question. First of all, you can type it into your calculator. If you type in ln and then activate the E button, E to the, and then just type in 3, you can type that all into your calculator and just get the answer. It'll equal 3. But watch, we can do this by ourselves. We can say, well, what is ln of e cubed equal to? Well, ln is really log base e of e cubed equals x. And if I change this from log form to exponential form, left to the right equals middle, e to the what equals e cubed. So I mean, if these two sides are going to be equal to each other, what must x be? It's got to be 3, because that way you have the exact same thing written on both sides of the equation. So again, x equals 3. So I guess my big message to you right now is that the power is to convert to the other form.
Number 18.
We will after we do 16 and 17. Yeah, we will. So folks, like, look at this one. We have log base 6 of 1. Okay, so you say, well, what is that equal to? I don't know yet. And that's log form, so you switch to exponential form, and you say left to the right equals middle, 6 to the what equals 1. And again, right now, you should all be able to answer that question. I mean, I did put this one up on the board, but in general, any exponential will only equal 1 if the exponent is 0. So x equals 0. This one, I can't contain myself. Super interesting. This is a great problem. So again, anytime you have something you don't know what it is, you say, well, that's equal to something. I don't know what it is. And now it's in log form. So now you say left to the right equals middle. 36 to the power of what equals the 4th root of 36. Now, who remembers how to rewrite 4th root? How do you rewrite any root as an exponent? It's not negative.
Fraction.
It's a fraction. 36 to the 1/4. Now, once again here, by the sheer logic, We want this side to be the same as this side. And the only side to make this side the same as that side is to replace x with 1/4. So that's just the logical force of two sides being equal to each other. Okay, let's skip 18. Kidding it. Okay, now, this one looks crazy. Right? I mean, just look at it. It's like log inception. We put a log in the exponent. That's enough to make somebody dizzy. So now watch. This is a real valid mathematical technique. When you're looking at something and you don't know what it is, what do?
Just give up.
You set it equal to x. Why? Because it turns it into an equation, and equations can be manipulated. So I say, I don't know what that thing is. I'll set it equal to x. Now, right now, am I in exponential form or log form? I am in exponential form because I have a base to an exponent. It just so happens that the exponent is also a log. But fundamentally, we're in something to the power of something equals an answer. So I'm in exponential form. Let's switch to log form. So remember, the first number stays the first number, log base 7. And then these two switch. So log base 7 of x equals log base 7 of 3. Now, by the sheer power and force of logic, if this is log base 7 of something, and that's log base 7 of 3, what must x be? It's got to be 3. There's no other way for these two sides to be the same thing. And so you just say x equals 3. Now, these are such great examples, not just of logs, but of math and problem solving. Because if you just walked up to this problem right here and you looked at it, your first thought would probably be to shut down, go home, have a snack, and take a nap. Right? Because, what's going on there? So, but if you just go step by step by step in a very slow motion and you say, well, you admit your ignorance. You're like, I have no idea what that thing is. Call it x. I don't know. Call it something. And then now you have an equation and you can rewrite it. You can say, well, this is log form, so in exponential form, it'd be left to the right equals middle. 36 to the x equals 36 to the 216. And now by sheer lame virtue of the force of logic, x must be 216. And so you see, you take a problem that looks tricky, but if you just follow your feet, teeny tiny little baby steps, you eventually get there. The key is not to feel overwhelmed and not to move. You have to move. You have to take a step. So look here at this thing. Should we wait for next class or should we do it? Might as well do it. There's one problem left. Okay, so what on earth is that thing? I don't know. Call it x. So now, what's ln really? 1. Log base e of 1 over root e equals x. Okay, so now this is log form, so convert it to exponential form. That's almost always the way. If they give you log form, convert it to exponential form. If they give you exponential form, convert it to log form. So now this is left to the right equals middle. I have e to the x equals 1 over root e. Okay, well, what's the square root of e? How do we rewrite a root? E squared. How do you rewrite a root? Fraction. So that's really, I'm going to come up here now. I have e to the x equals 1 over root e. But that's really e to the x equals 1 over e to the 1/2. And then what did we say about doing a reciprocal? Anytime you wanted to, you just change it to a negative. And that's allowed, that's a valid move. And therefore, if you want the left side to be equal to the right side is already e to the negative 1/2. E to the what? Negative 1. This was some very interesting, different problem solving. And folks, your homework due by next week is to finish all of chapter 5 and more. So you can now finish all of chapter 5. We went through quite a few problems today together. When you get home, email me your questions about any of them. Post it to the forum. That's next week. Next week, we're going to do the whole week, chapter 6, and then the following week, Monday, is when your test is. All right.
Interesting fact. We know that E equals 2-point continuation, right?
Yeah, 2.71.
Right. But apparently A equals another number as well. And it's like 0 points. I found that out like recently. It's crazy. I found it out.
You mean that whatever equation E is the solution of, that equation has another solution?
Possible.
Well, where did you find that out? What's your source?
Well,
Because right now my tendency is to tell you,
I'm wrong.
I don't believe you. No, I wouldn't call you wrong. That's a little mean. I just say I don't believe you.
I'll look it up. I'll show you.
Better yet, I'd say I'm not convinced. That's the
Let's already
nice
close
way.
it down. Let's already close it down. I'll show you next class.
Okay.
If I remember.
Yeah. Oh, I definitely want to know, Lee, because I'm always willing to admit that I'm wrong, or just that I've never heard of it.